Okay. I think I'm recording. There's my... Hold on. Okay, we're recording. Here we go. All right, let's get started. We're talking here about limits that fail to exist. All right, everybody with me? We're on page 2, limits that fail to exist. Okay. So what we're going to talk about is when does the limit not exist, right? And the limit does not exist. Page 2. Page 2, limits do not exist. Adrian, go away. We're going to notes page 2, please. Thank you. Over there. Yes. Okay. So there's going to be 3 situations when a limit doesn't exist. All right. The main idea, which we saw yesterday, right, is that you have to be coming toward the same value from both the left and the right. That's the main idea of a limit, right? So from both sides, coming toward that value, that's when a limit exists. So one of the main things is this first reason of when a limit will not exist, and that's when the behaviors are different from the right and the left. Or what does that mean? It means that they're coming at one value from the right and they're coming at a different value from the left, right? They're not emerging toward that same value there, okay? So that's the first reason of when a limit isn't going to exist. So let's take a look at this graph. The square root of x over x. Do you guys know what that graph looks like? Okay, this is one you'll do want to memorize. We haven't seen it in a while. Remember what it was like?
A line of positive on that.
Yeah. Yeah, exactly. So it's going to look like this. You're going to have a line, like if you just plug in a few values here, see what happens, right? So if I had like x equals, I don't know, let's start with like -3, right? Plug in a -3 here. Well, you get +3 over -3, right? And what's +3 over -3? Well, that's just -1. And how about if I plug in a -2? I'm going to have +2 over -2, so that's, again, -1. And what if I plug in a -1? Well, +1 over -1, so again, I'm going to have -1. What if I plug in a 0 here? 0 over 0, which is no solution. You can't ever divide by 0, right? What's going to happen when I start plugging in positive values? It's just going to be +1, right? 1 over 1, 1 over 1, 1 over 1. Okay, so this looks like this. It looks like a little hole here. And then for all these at -3, -2, -1, I'm all down here at -1. And then for all my positive ones, 1, 2, 3, etc., I'm over here at +1. And at 0, notice those are open holes because it doesn't exist at 0. All right, so looking at this chart, it's kind of the same chart we just did up there, right? -3, -2, -1, oh, whoops, whatever, -0.5, it doesn't matter, okay? You're going to have all -1s here, okay? And then over here, it jumps to 1s. So what's that limit? Well, these are all coming at -1 from the left, and from the right, they're all coming at +1. There's not that similarity, right? They're not approaching the same value there. They're approaching different values from the left and the right. So this is where we say that this limit, DNE, or does not exist. Because from the left, here's my left-hand limit, I'm going toward -1. And from the right, I'm going toward +1. And so since my left-hand limit and my right-hand limit are different, we say that the limit does not exist. Does that make sense? They've got to come toward the same value. They've got to approach that same value for a limit to exist. Okay, good. So that's the first case of when a limit doesn't exist. A second case of when a limit doesn't exist is this next one here, what's called unbounded behavior. So what does that mean, unbounded behavior? Well, an example would be the graph of 1 over x squared. Bless you. What does the graph of 1 over x squared look like? Go back to our rationals, right? We've got to have an asymptote somewhere. Where's our vertical asymptote? 0. We have a vertical asymptote because this denominator, right, gives us a vertical asymptote of x equals 0, right? Okay, so vertical asymptote there at x equals 0. Is there an x-intercept? No x-intercept. How about a horizontal asymptote? A horizontal asymptote is also at 0. Y equals 0. Why? Because the degree of the numerator is 0. Degree of the denominator is 2. Numerator degree is smaller. How we get horizontal asymptotes? We got to review graphing, huh? Okay. Where are these branches? We have some branches on these, right? Where are the branches? If you're not sure, plug in a value, right? Like plug in a 1, right? I would have 1 over 1. Oh, so that'd be up here. Plug in -1. What would you have? -1 squared, +1. So our two branches go like this. Okay. This should be one of your basic rational graphs, 1 over x squared, that you guys should be able to graph without even thinking about it. Right? This should be one that we just look at that, oh, 1 over x squared, I know how that goes. Kind of like 1 over x, right? You guys know 1 over x is the one with the two branches that are opposite, right? 1 over x, you've got the one branch here in quadrant 1, and you've got the one branch down here in quadrant 3. Right? So 1 over x squared just flips this one to make everything positive. Remember that a little bit? Okay, so this is one where we want to look at the limit as x is approaching 0 in the middle, right? Well, what's happening as I'm approaching it from the right? What am I going toward? What are my y values going toward?
Infinity.
My y values are going toward infinity, right? How about on the left-hand side, what are my y values going toward? Infinity. So what we could say for this one is that our limit is infinity, right? And later on when we get into some more details with limits, we are going to say that. We're going to say that it's infinity. For now, because infinity is not a real number, right? Technically, it has to equal a real number to be a limit. So since infinity is not a real number, this is a case where we'll say because these are both going toward infinity, we're going to say that that's a limit that does not exist, right? So that's what's called unbounded. Unbounded means that it's going toward infinity, right? That it never ends. Sometimes you're going to see this where one goes toward infinity, one goes toward negative infinity. Same idea, right? There's not an actual limit because they're not going toward a number. Does that make sense? And so here, like for example, if I wanted to plug in some numbers on this one, you can really pick any numbers, I don't know, like -2, whatever, -1, -0.5, -0.25. Just kind of picking some random numbers here that are getting closer to 0, right? Well, this would just be like 0.25. What is that? That's 1. That's -1/2 squared, so that would be 4. This would be 1/4, 16. Is that right? Kind of just did that in my head. But again, these numbers are getting bigger and bigger and bigger, so they're going toward infinity. And so since it's not approaching a real number L, as it approaches it, we say that it does not exist. So we call this a DNE. Now, later on, if you wrote like on a test or something that this limit was equal to infinity, to positive infinity, I would totally say you're right. Like, that's okay to call that infinity. Technically, the limit doesn't exist because it's not a real number, infinity, but I do see where you're saying they are both going toward infinity, so that's okay. Make sense? Yeah?
Aren't they technically approaching 0 though?
No, we're always talking about the y values. So what are your x is approaching 0. Here it is. X is totally approaching 0, right?
Yeah.
But what are my y values approaching? Right? So look at this chart. X values are approaching 0. What are these y values approaching? These y values are getting bigger and bigger and bigger. So your limit is always for the y values. Okay? So we've got to kind of get that in our brains. All right? That limit is always referring to where your y values are. All right, the last example, and this is a very rare example. This does not happen often. It happens in these random graphs where we have what's called oscillating behavior. What does the word oscillate mean to you guys? Physics. Yeah, what does it mean? Like swinging, kind of bouncing, right? Oscillating back and forth, right? So that's what that means in the same thing in this graph. And so let's take a look at this graph, sine of 1 over x. Now this is one we don't know how to graph by hand. But I want us to go ahead and take a look at it here on the calculator. So I'm just going to type it in, sine, oh goodness, I need new batteries. Sine of 1 over x. All right, so let's take a look at what this guy looks like when we graph it. Whoa, okay. So there's something going on the inside here in the middle. See that? Okay, and it kind of did this little like boop, 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 boom. It kind of looked like a heart monitor almost, right? I'm going to just zoom in a little bit so you can kind of see what's happening in the middle there. Whoa, kind of cool, right? Okay, so the sine of 1 over x is kind of a normal graph, so you can kind of graph it like this, right? It's kind of normal, it just comes in like this. And then as it gets really close here to 0, it starts doing this ba 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 thing, like this crazy thing, and then it comes back down. Exactly like that. And it makes those sound effects too. Right? All right, so it does this, and this is that bouncing up and down. That's that what we call oscillating behavior. Again, it's very rare, but it will happen every once in a while, usually with trig graphs is when you see this. Yeah?
Why does, I don't know if my calculator shows it wrong, but mine doesn't bounce as much as yours.
So it's probably, do the Zoom 7, do a Zoom trig.
Mine doesn't bounce at all.
Are you in radians? So be in radians, do a Zoom trig.
Oh, okay,
Better?
that's, well, now it bounced up once, twice.
A little more?
Yeah.
Maybe zoom in.
It's
A little more.
Wait, do you want to be in radians or
You want to be in radians for sure.
Look, like,
oh, okay, that's
I
why.
did another zoom in.
Oh, okay. I
I'm
was
making
about
it will
to
look like my
be
window range.
Yeah, do Zoom 7, which is Zoom trig, and that'll get you some trigs.
Yeah.
Oh, 6 is, oh, you can always do
Whatever.
Okay, yeah. Oh, goodness. What is that? Oh, you're just playing. You're just zooming in. Yeah, if you zoom in a bunch, you're going to just see, like, right? Craziness. Okay, so let's fill out this table. They gave you some specific ones. So they told you try 2 over pi. All right, so 2 over pi was at 1, which is kind of interesting. And then they said try 2/3 pi, or 2 over 3 pi. Is that 2 over 3 pi, or is it 2/3 pi?
We'll never know.
I know, let's try it. Nope, I think it's supposed to be 2/3 pi. Yeah, that's maybe right. I don't know. And then 2/5 pi? Oh, I wrote the wrong one. Where did I get that? Ah, I need new batteries.
Wait, is the first one 2 divided by pi?
I think it's 2 divided by pi. Yes, that's what I did. 2 divided by pi. Yes. And then the next one, 2/3 pi? 2/3 pi. Okay, so that was point. Right. And then 2/5 pi. Which was 0.714. And then 2/7 pi. And then 2/9 pi. Okay, the whole point of this, what we should be noticing, right, is that these aren't really doing anything. Like it goes down to 0.4, then back up to 0.7, and then down to 0.1, and then to 0.1. There's no patterns here. There's no rational behavior, right? They're bouncing up and down. They're going all around. And so what we'll say, since they're not emerging toward any value, it does not exist. So this is that oscillating behavior. Again, this doesn't happen very often. But every once in a while you'll see it, and it'll just be with a random weird trig function usually, and you'll see that oscillating behavior. Okay, so at the top of the next page, it just kind of captures these 3 concepts in one little box. So right here, it's the common types of behavior associated with the non-existence of a limit. So the 3 things where we can see that we can write does not exist. And sometimes we get like DNE happy, and we want to just say doesn't exist all the time. There's really only these 3 behaviors where you're going to actually say does not exist. The first one is that it's a different number from the right than it approaches from the left. Okay? Second one, increases or decreases without bound. That's the infinity or the negative infinity. Okay, so you're seeing it going toward that vertical asymptote of infinity or negative infinity. And then the last one is that oscillating behavior. So that bam, 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 like up, down thing. Okay? And those are the three cases as of right now where you will put does not exist. Questions? Okay, so that's it for notes. I'm going to get you guys started on your homework, but let me turn off this video real fast.